Okay, so we'll be recording this for everyone who couldn't make it. We're going to work on problem number 19 on the test first. Alright, so this ball is being twirled, is the word, in a circular path. This is 75 centimeters, but since I know it should be in meters, I'm going to change it right away. It has a velocity of 5 meters per second. Draw a force diagram or free body diagram, same thing, for the ball at the top and the bottom of the circle. So to start with, I'm thinking this has gravity down, which is the weight of it. And it also has the string pulling down, which is tension. And those are the only two things. Now, a lot of people on the test put they put in arrows for like the velocity, but the problem with that, it's fine if you want to put arrows over here, but if you put an arrow here, then you're saying it's a force. And there's not really a force on this thing sideways. So if you're going to put arrows, put them over on your picture, but not on the force diagram. On the bottom, then, we have the same weight down, but now the rope is pulling inward, and so it has to be a lot bigger. I know that it has to be bigger because I'm thinking if this rope was just hanging here, not even moving, then the weight down would have to be balanced by the tension. For it to be moving in a circle, it has to have more force inward. So that's how I know that one is bigger. So this is the first part for the force diagrams, part A. Part B, what is the tension in the cord when it's at the top? So I start with force equals mass times acceleration. And it's radial acceleration because it's not slowing down or speeding up, it's just turning. So you can think of that as a radial force. And I know that that is v squared over r. So when I put that in here, I get this. So that's just kind of like generically, I need an inward force to make a mass move at a certain velocity on a certain radius of turn. Now I ask myself, what is supplying the inward force? Well, when you're at the top, it's the weight plus the tension together. So these two are on this side, and I get that. And we know that the weight is just the mass of the object times gravity field down. So I could just write this as tension plus mg. I'm just reversing these, equals this. So tension plus the mass of this thing is 4 kilograms. So that means its weight is 4 kilograms times 10 newtons per kilogram of gravity. So 40 newtons. So the tension plus 40 newtons of help from gravity equals the 4 kilograms times 5 meters per second squared divided by 0.75 meters. Now earlier I said this had to be meters because, well, I didn't really say why. It needs to be meters though because the velocity is in meters per second, not squared. And I need the meters to cancel out. So this is 25 times 4, which is 100 divided by 0.75 is around 133 newtons. So the tension plus 40 newtons of weight has to be equal to 133. So the tension must be just 133 minus 40, or 93 newtons. Now on the bottom, it's the opposite. It is tension minus the weight that supply that same inward force. And mv squared over r. We know the mass isn't changing, the velocity isn't changing, the radius isn't changing, so this is still 133 on this side. But the difference is I'm subtracting 40 now first, and then then needing 133. So add 40, so the tension must be 173 newtons when it's at the bottom. Now the last part is saying if the cord has a tension maximum, I guess this is part C, tension maximum of 250 newtons, then what is the fastest it can be twirled without breaking? Well, it's going to end up breaking, if we look at my picture, at the bottom first, because that's when the tension is the largest. At the top, gravity is helping, tension is not as big. So this is going to happen at the bottom when I had tension minus the weight equals this business. So now this is 250 maximum minus 40 newtons. I'm running out of space here. So this is 210 newtons equals mass, which is 4, times the new velocity that I don't know, divided by the same 0.75 meters, and multiplying 210 by 0.75, I get 157.5 equals 4 times v squared, dividing by 4. Sorry, that's not an equals there. And I get 39.375 is v squared. Then I square root it and get v is 6.27 meters a second. I gotta blow my nose here. Which is always bad when you have to do that on video. What's that?
Can't you just pause it?
Probably. I don't remember how on this. At least I didn't do it right into the microphone. Does that help?
Mm-hmm.
Okay, any other requests?
I have a question.
Okay.
I think it was part B.
Okay.
But when you did 4 kilograms times 10 newtons per kilogram, is the 10 the same as gravity?
Yeah, there's two ways to do gravity. You can either write it newtons per kilogram, or you can write its what acceleration it causes, 10 meters per second squared.
So that's just like the force version of it?
This is the gravity field, the force per kilograms versus what it causes, 10 meters per second squared of acceleration. You can use either set of units and it works out to be the same.
Okay.
So I like this one just because it makes more sense to me to be plugging that in, but they really mean the same thing.
Okay.
Any other questions from the test or anything else? Yeah, Ben.
Can you run through a problem that is similar to this? It blocks one block.
Sure.
So do number 10 then.
Number 10 is that way?
Yeah.
Well, let's do 10 first, and then I'll do a similar one that's Atwood's machine is what that's called. Because 10 is kind of a lead up to that. Object with a mass of m slides down a rough 37-degree incline. Coefficient of friction, kinetic, is 0.2. What is the acceleration of this thing? So I'm first thinking to myself, okay, gravity's pulling straight down, and I can think of that as partly going in.
Conference room 3. Ms. Curtis, Mr. Carter, Ms. Bird, Mr. Goff, Ms. Steglich, Mr. Rasmussen, that's in conference room 3. Thank you.
So gravity's pulling straight down. I don't know how big it is because I don't know what the mass is, but I know that whatever the mass is, times it by gravity, and I have the weight. I need to take this one and figure out the components here. So I know that this is 37 degrees here, but I'm going to draw this bigger. And I'm going to slide this down to here. mg, so then using sine and cosine, this one's going to be mg sine of 37 because it's the opposite. And this one's going to be mg cosine of 37 because it's the adjacent. So I still don't know what the numbers are, but at least I have an expression for them. I know the normal force here looks like that, and it's going to balance out this, and whatever the friction is here, that's going to be taking away some of this. I'll make that a little shorter. But it's going to take away some, but it's not going to balance the whole thing out because this thing appears to be accelerating down the hill. So this needs to be bigger than that. So the normal force is going to be the same thing as this component. I need that because I need to know what friction is, which is mu times normal force. Wow. I don't want to be too shocked on video, but so 0.20, and then we have mg cosine 37 for friction. This component is mg sine of 37. So I still can't solve it yet, but I'm hoping that things are going to cancel out and let me solve this. So the acceleration would be the sum of the forces, or the net force is another way to say that, divided by the mass. Well, the vertical ones cancel out of the ones in the y direction, but I've got mg sine of 37 pulling down the hill minus friction, which is 0.2 times mg cosine of 37 resisting, fighting it up the hill. And there's an m on the bottom, which is just what I was hoping because now all the m's cancel out. Which means then the acceleration is g, which I know, times sine of 37 that I can plug into my calculator. 0.20 times g, which I know, times cosine of 37, which I can plug in again. So I can figure out what this is. I was hoping I'd already done that somewhere, but I haven't. Okay. So we've got 10 sine 37 is 6.02, and then we have 10 cosine of 37 times 0.2. This is 1.6 basically, with rounding. So that's like 4.4-ish meters per second squared. And if we look at the test, that is 4.3. They used 9.8 probably. I used 10, so we're close enough. Okay, so the follow-up question is let's solve this same problem but pretend like it's not on an incline. So I guess it's not the same problem. We'll make up a mass because we do need it for this. Let's say 3 kilograms. Some kind of pulley here. And we'll say it's pulling something here that's 9 kilograms. This is supposed to be flat here, but it's not very well drawn. And I want to find out the acceleration of this, and the coefficient of friction will go with the same 0.2. So my first thought here is I need to come up with a force diagram. So on this sliding brick, I have the weight down and the normal force up. Call it weight 1. Those are balanced. I've got some kind of a tension pulling on this thing this way with some kind of a friction back resisting. which is very similar to what I did up here, just it was on an incline. And then on the second one, there's only two forces, a larger weight, call it weight 2, and then we've got the same tension up here that that one had there. But I know that that tension has to be less than the weight because this thing needs to be falling, and if the tension is the same as the weight, then it's either not falling or it's falling at a constant speed, and I don't think that's the case. So I've got that. Let's find some forces here. We can get the weight is mass times gravity, so that is 3 times 10 or 30 newtons, which tells me the normal force is the same thing. And once we've got that, then I can find friction, which is mu times the normal force, 0.2 times 30 newtons, which is, what, 6 newtons? So now I know that this is 6 newtons back. For that, the weight of the second one would be mass times gravity, or 90 newtons. And I think I have enough that I can figure this out now. So what I can do is pretend that these are one unit that is slurping together over the edge. You can coin me on that phrase if you like. So when I do that, then they do have the same acceleration because they're hooked together. So this is going to accelerate this way the same rate that this one accelerates down. So when I say they're together, then I don't care about the tension force, which is the advantage because I don't know what it is. So I can't really deal with it yet. So I'm going to get rid of it by lumping these as one big thing that goes over the edge. So when I do this, now I have something pulling back here, which is friction, and I have something trying to pull this way, which is the weight of that one. So that is the two forces that determine the acceleration. So I've got the 90 newtons off down the edge there, minus 6 newtons that way, divided by the mass of both of them, which is 12 kilograms. Which gives me 90 minus 6, or 84 newtons, divided by 12, which ends up being an even 7 meters per second squared for the acceleration. Follow-up question typically then is, okay, now that you've found the acceleration, what is the tension between them? And when you do that, you have to treat one of these separate. So I'm just going to treat the bottom one. Well, I've already drawn the picture there. Just deal with that bottom one and say, okay, it has a force that produces an acceleration, and the force on this is 90 newtons down minus the tension force back up. That's the net force, producing on those 9 kilograms a 7 meter per second squared acceleration. So rearranging this, I could then find that that needs to be, what, 27 newtons? Or that it is 27 newtons for the tension? Does that make sense? Okay, let me stop this and see what all these other people want in here.